Hey everybody, welcome back to Natty Sci. You know, we have 3 weeks ahead of us, and so I want to do everything that I can to help you to stay engaged. Up on the board, I went ahead and put what all the summative grades are in the grade book, and so there are currently 4, and we are going to add a 5th before the end of the semester. So Natty Sci summative grades are listed up there. If you are missing any of those, you can affect your own grade by contacting me and setting up some way for us to get you caught up, okay? Given that we're gonna be kind of on a weird schedule system for the next 3 weeks, assigning you to me, you know, it could be a possibility, but that might only happen one time during the entire 3 weeks. And so if you have an open mod and you see that I have an open mod, you could come in and take a test that you are missing. So keep that in mind. To keep you engaged during this time, I've decided 2 main things for natural science. The first is that I want to make sure that we are learning about things that I know that you are interested in. So the bulk of our focus during the next 2 weeks of instruction is going to be all about, mostly about aliens, what we do to detect aliens, why we haven't contacted aliens. There is a scientific series of steps that we've gone through for decades to have a better understanding of how likelihood we are to find aliens out in the cosmos. Now, before we do that, there's one last little piece of broader understanding of the universe and how the universe has formed over time that I'm going to get you during the first half of class right here. Okay, we're going to learn a little bit about how stars form into large conglomerations. Okay, Angela, if you could just shut your computer, thanks. And also, what have we learned about the origin of the universe itself? So what I've done in your handout, and I'm going to sort of follow along with you because I've deliberately put some gaps in your handout so that you would have something to do. And when we write things down, it can increase the chances that you understand it. But folks, I don't ever want us to have to take a ton of notes. You're going to see that you're going to have to write down over this mod the equivalent of like 5 sentences worth of stuff. That's it. Okay? So if you have a writing utensil, great. If you don't have a writing utensil, there's extras in the back of the room. And let's go ahead and get started. So, one last thing, my bad. People are going to ask during this time, what is the final for natural science? There is no official final for natural science. It is a unit test. And for all of us, the blue box on the whiteboard, the red text, I should say, that last summative grade we are going to add in large group the last week of school. So it's going to be super important that you attend that large group because that is where the last measurement for the semester is happening. Basically what it comes down to, folks, is that by the Friday right before break, if I don't have your work, it's just going to have to stay as a D&D, and that would have a negative impact on your grade, and I don't want that to happen. There's no reason why it should have to happen. I want to help you, but you're going to have to see me outside of class in order to make it happen. Okay? So, the universe is huge, and one of the things that I want to point out to everybody, and you know what, let's just try. Do you want it darker?
Yeah.
Are we gonna stay awake if it's darker though? That's the
because it's out of space.
That's right, Brecken. Okay, and so yeah, no, I like it being a little dark here. It looks really good on camera. And so, what are we looking at here? Space. What are these objects?
Stars.
Brecken, they're actually not stars. Okay, stars is a really, really good guess, and Brecken, nice recovery. Yeah. These are galaxies. If you want to know how big the universe is, the short answer is that it's flippin' huge. The longer answer is that stars form into groupings themselves via the pull of gravity. So you know how in our solar system planets are orbiting a star, which is our sun? Those stars in the cosmos are all attracted to each other by the pull of gravity, and they come to form large objects called galaxies. This is a very famous photo. This photo is from the Hubble Space Telescope, and basically we pointed the Hubble Space Telescope at a segment of sky that looked empty to us, and we found, thousands of galaxies, no big whoop. Okay, the universe is huge. It's estimated that there are hundreds of billions of galaxies in the universe. Okay, so space is really big. What is a galaxy? This is something that you're going to write down. Okay, a galaxy is collections of either billions or trillions of stars, depending upon the conditions under which it formed. This is on page 1 of the handout that you picked up when you walked in. No worries. Okay, and the key thing, remember, during our stars section, and unfortunately we didn't have a lot of time to talk about this year. We would normally spend an entire week on black holes. But black holes are the strongest pull of gravity of any object out in space, any region of space. And there is a black hole at the center of every galaxy. That is something that has enough gravitational pull to have hundreds of billions or trillions of stars orbiting around it. Right now, our galaxy is the Milky Way. We are a collection of 400 billion stars orbiting around a central black hole. Okay? So just because a black hole exists doesn't mean that it's dangerous. Just like we learned with gravity at the beginning of the year, gravity is mostly dependent upon distance. If you're far enough away from something that has a strong gravitational pull, it doesn't mean that you aren't affected by it, but it also doesn't mean that you're going to be pulled into it. And so we are orbiting a black hole right now, as we speak. Our sun is anyway, and then we're orbiting our sun. And you know, galaxies come in 4 flavors, and I'm going to go through these pretty swiftly. You do need to know the shapes of these flavors for our last summative test. And so probably one of the most common galaxy types is a spiral galaxy. We have a central bulge in the middle, which is a lot of stars and light that are orbiting that central black hole. And then we have a disk of gas and stars orbiting around the outside, usually in this pinwheel format. The nature of gravitational attraction tends to result in this pinwheel format. And so here's what a spiral galaxy looks like on its side. And note that these are all galaxies that we see far away from us. We live in our own galaxies. It is literally in our own galaxy. It is literally impossible for us to take a picture of our own galaxy, because you know how, like, if you're inside your house, you can't take a picture of the outside of your house while you're inside your house? Same concept with the galaxy. We would have to travel so far away from our galaxy to get the entire thing in frame that it's basically an impossible task. Now, that doesn't mean that we haven't learned a lot about the shape of our galaxy by observing the pattern of stars within it. So this is the Andromeda Galaxy. This is the closest spiral galaxy to our own, the Milky Way. It's about 2.5 million light years away. So when this photo was taken, the light had left Andromeda 2.5 million years ago. Space is about 14 billion light years across and expanding. And so it's possible that even for close objects, you look at an object and the light left them when there were still dinosaurs walking on the Earth. Okay, space is humongous. Barred spiral galaxies are spiral galaxies that have this central bar in the middle instead of just a bulge. There's still a black hole in the middle, but the central portion is in a bar-like shape. And then we have, once again, the spiral arms, the disks of gas and dust. Sometimes there are binary spiral arms, like in this one, just 2 of them. Sometimes there are more. Here's some facts about our own galaxy. We are 26,000 light years from the center of our galaxy. Remember large group before we went on break. That's how a light year is how far light travels in a year. So it takes light from the center of our galaxy 26,000 years to reach us. And our galaxy is about 100,000 light years in diameter. From one end of our galaxy to the other, it's 100,000 light years. Brecken, you got a question? Just stretching? Okay. It takes us 200 and 250 million years to orbit the center of the Milky Way galaxy once. The dinosaurs developed and became extinct all within a time span before we had orbited the Milky Way once during that time. We are traveling right now at 155 miles every second orbiting the galaxy. So 155, 155, 155. Okay. And you can actually see the edge of our galaxy on a clear night. You have to be far away from cities. Okay, it looks like a milky haze across the sky. And it has to be a really remote area because we have what's called light pollution, where light from cities actually blinds us from being able to see the gas, dust, and stars that make up the edge of our galaxy. But you can see the edge of our galaxy from Earth under the right conditions. So Milky Way is a barred spiral. Like I mentioned, we don't have photos of our own galaxy, but this is a pretty good model of what our galaxy looks like based upon mapping of stars within it. And you can see that our sun is located on an outer spur. It's called the Orion spur of our galaxy, one of those outer arms. So we know where our sun is within our galaxy. An elliptical galaxy is all bulge. They are mostly made up of stars but no gas, and that is a clue that tells us a lot about the development of galaxies. Think of it this way. An elliptical galaxy is a galaxy that is mostly stars but very little gas because all of that gas has been gobbled up through the pull of gravity into stars. So we know, in the same way that we know the law of superposition, a rock layer that is under another layer must be older and would have been laid down first. Same concept here. If we know that there isn't much gas in a galaxy, that galaxy has had more time to suck up all the gas, and so is an older galaxy. So elliptical galaxies are amongst the oldest of galaxies. Spiral galaxies are amongst the youngest. Brecken, I need you to leave that up, please, sir. Thank you. This is an irregular galaxy. This is likely formed at a point in which two galaxies are merging with each other. Because if gas and dust can be attracted together via the pull of gravity, and stars can be attracted towards the pull of gravity, galaxies are attracted to each other via the pull of gravity as well. And so galaxies merge with each other. It is not a violent situation. It's kind of like if you were to mix two different types of cereal together in a bowl. Okay, all of the different stars will intermingle with each other and eventually form a larger galaxy. The closest galaxy to us technically isn't the Andromeda Galaxy. There is a little miniature galaxy called the Canis Major Irregular Galaxy that is orbiting just above the northern pole right here. So we have a tiny galaxy that is in the process of merging with the Milky Way, and so you can see the stream of some of the gas, dust, and stars that is in the process of merging with the Milky Way. So that is technically the closest galaxy to us because it's in the process of merging with the Milky Way. So where did all this matter come from? Where did all the gas and dust that was in the universe that formed stars come from? Yeah, if you turn to this page, there should be a point for you to write something down here under top right on page 3. So, Big Bang is a well-supported and researched theory. Remember, a theory is a big deal in science. A theory is not, I have an idea. A theory is not, I'm guessing. A theory is, I have a ton of evidence, but we are open to collecting more evidence to refine our theory. Okay? Hypothesis is most equivalent to an idea in science. Okay? Theory is a big deal. The theory of the Big Bang, the theory of evolution. Okay? We are pretty darn convinced that we know how it works. We are just seeking further refinement. Okay? A law, on the other hand, is something that we know definitively because it's not complex and it works the same way every time. The law of gravity, the law of ideal gases. Okay, works the same way every time. So the Big Bang is a well-supported and researched theory that describes what happens after the universe was created. Okay? We don't know why the universe came into being. Okay? Science can't know what happened before the Big Bang. We have the universe tracked down to microseconds, milliseconds. Microseconds are smaller. Microseconds, I think even nanoseconds. No, maybe microseconds. Microseconds to when the universe formed. Okay? We know what it was like. And I'll show you an image, I think, coming up here shortly as to how we know that. Okay? It was one of the landmark discoveries. And it's based upon observations and analysis. Showed up for reasons we don't understand, but we can still think about it logically and interpret the evidence that we do have. Okay. I do want to point out to you that this slideshow is available in full on Google Classroom. Everything for the next 2 weeks is available in full in Google Classroom. So all matter in the universe quite suddenly comes into existence about 13.7 billion years ago. The early universe was probably entirely photons, particles of light, and other forms of radiation. I'm going to map this out for you here shortly. We're going to skip this what happened slide because it's pretty dense. Instead, I'm going to showcase it for you on the board, and I will move the camera here so that we can see the board as I explain it for you. This image is how we discovered the early formation of the universe. This is the cosmic microwave background radiation image, and basically there becomes a point where when you gaze with telescopes of different types, and under this particular situation, a microwave telescope, you're going to read about different types of telescopes while you were at home this week. Microwave telescopes eventually get to the point where you don't see anything but this out in space. And that's an indication to us that that is the origin of the universe. The event that caused the origin of the universe. Now I'm going to turn the lights back on and shift the camera over here. That's looking good. Okay. So, I drew the diagram up here on the board. We have the Big Bang happens approximately 14 billion years ago. This number is continually being refined as we get more data. Okay? It starts off very compact. Based upon what we see in that microwave background radiation diagram, we are seeing large amounts of light at the origin of the universe. We call it radiation dominated. It's very compacted together, and since it is compacted together, that light is running into itself and slowing itself down. And when you slow light down, Einstein had a very famous equation for this. Okay, and you probably know it, but you may not have understood what it means. And maybe you do understand what it means. Who's seen this before? You might have seen it before, maybe not. This equation basically is one of the most fundamental equations of physics and astronomy because it explains the relationship between energy and matter. E equals mc squared. If you take matter and accelerate it to the speed of light, and we square it in the equation, matter becomes energy. It works the other way too. If you take light and slow it down enough, you produce protons that form into the first hydrogen atoms. And so the universe starts very compact and radiation dominated. It starts to spread apart and then become matter dominated. Now, yeah, there's light, lots of light in the universe right now, but in terms of overall quantity, we are in a much more matter-dominated universe than we are in a radiation-dominated universe right now. And I mean, you know the rest of the story. These hydrogen atoms that were formed are pulled together by the pull of gravity, formed helium atoms. Those hydrogen and helium atoms, if squished together tightly enough in the core of a star, form larger atoms. So here I've indicated that there was a process that eventually led to a supernova, right? We had a very large main sequence star from a very large nebula, becomes a red supergiant, which goes supernova. That supernova ejects heavy elements to our region of space, and that gas and dust eventually forms into our sun and Earth. This is about 4.52, I should mark that down. This is about 4.52 billion years ago. BYA is billion years ago. And now, we're at now. Everything that's happening now is happening now. What happened to then? We passed it. When? Just now. When will then be now? Soon. So, switch the camera back over so we can keep rocking. Okay, lights out. So, stars are going to form different shaped galaxies depending upon the circumstances in which that galaxy forms. If stars are using up all of the nearby gas because maybe they're rotating slowly and so gravity has a chance to pull that gas together, you get elliptical galaxies. If stars are leaving some gas behind, it's probably because they're rotating too quickly to draw it in, and you get barred spiral or spiral galaxies. There are two main hypotheses for how galaxies form. One is the top-down hypothesis, the other is the bottom-up hypothesis. Top-down hypothesis is that one huge collection of gas builds a galaxy and all stars within it simultaneously. The bottom-up hypothesis is that small groups of stars merge together and form larger galaxies. This is an active field of research. It may be one, it may be the other, it may be both. Current research, if I recall correctly, tends to favor the bottom-up hypothesis, okay? That stars form first and then are drawn together by the pull of gravity. Okay? Over time, galaxies are getting far away from each other. You're going to watch some short videos while you're at home that will help you to understand this. By analyzing and understanding light, we can know the direction and speed of different objects out in space. We are not guessing about this. We know because we are careful in understanding light and how light works. So, everything in the Big Bang starts in one giant clump, and we have evidence that the clump cools down. A good question is, what other evidence, happens? What other evidence do we have to support the expansion? And we understand how light behaves. Okay. I don't think we have time for this today, unfortunately. I'm going to have to skip this one. Okay, does any of you know who Felicia Day is? She's like a famous internet game person. Anyway, she's talking about galaxies. Unfortunately, we're a little short on time because #pandemic.
Don't we have another period?
We do, but there's a completely different plan for second half. Okay?
Oh.
Yeah, I want to keep you busy, Angelo, this whole time. Okay? So, just a reminder, here's the electromagnetic spectrum that we're returning to. This should look familiar to you right now. To be fair, this electromagnetic spectrum is flipped from how I showed it to you in large group. In this one, gamma rays are on the left and blue light of the visible spectrum is on the left, and radio waves are on the right and red light is over here. Our understanding of visible light has helped us to understand what information we can glean about the motions of galaxies out in space. And there was a very famous astronomer who noticed this called Edwin Hubble, and we named a huge freaking telescope after him because it was amazing and awesome. And what Hubble basically noticed is that galaxies that he was seeing out in space, and he only did this with about a dozen galaxies. He was doing this work in the 1920s, okay, when we had pretty good light telescopes, but that was about it, okay? And he noticed when he was viewing galaxies in his telescope that they had either reddish or bluish tinges. And most of them had reddish tinges. Okay, what does that mean? Well, what do we know about red and blue? Well, red light waves by definition are more spread out. Blue light waves by definition are more bunched up. And that is a clue to us as to what is happening with the galaxies that we are observing. Okay, so that's a train, right? You all know from experience whenever you hear anything, like let's take like an ambulance siren as an example, okay? And I'll do it for everybody here in class. You get that change in pitch that happens when an object moves past you. If you are into car racing, that shows itself as the car moves past you, right? That's what we call the Doppler effect. And it's true for sound. We can experience that at any time. It's also true for light. And this is kind of a detailed and complex description of it that I'm not going to go through point by point. because I want to make sure that, you know, we keep our sanity, and a lot of reading can be a problem. But there is a point where you need to write. No, I was smart enough not to have you write anything on the busy slide. That's good. So, long story short, TLDR, too long, didn't read, is that when an object approaches you, the visible light waves in front of it tend to get bunched up and tend to be blue tinted. When objects are moving away from you, the light tends to spread out, and spread out light is red tinted. So you can know what direction an object is moving in space, even for very different distant objects, by measuring the exact amount that they are red tinted or blue tinted. And the more red tinted an object is, the more those waves are spread out, and the faster the galaxy is moving away from you. The more blue tinted the waves are, the more bunched up those waves are, the faster that galaxy is moving towards you. Andromeda is slightly blue tinted. Most other galaxies are red tinted, and the farther they are away from us, the greater the red tint, indicating to us that as far as we can see from our present understanding of the data, our universe is expanding and will continue to expand. Okay, and then on this slide, this has a summary of everything that I've just described with redshift. We don't have to go through it point by point. The point is just for you to have a record here. Okay, so if I were to summarize the universe, okay, in this image, Big Bang happens here. Universe is mostly radiation dominated at the beginning, but as that light collides with itself, it slows down and becomes matter. And then the universe is matter dominated from that point on. Stars and galaxies form and spread apart from each other. And right here at the top of the diagram, where we are right now, we see a matter dominated universe with galaxies that are mostly red shifted, showing that they are moving away from each other and the universe is expanding. This isn't guesswork. Okay, this is based upon measurements that we are taking out in space. Okay, I can skip that one. Okay, now, this is an active field of research, as most scientific fields are. Okay, and so a lot of people ask the question, well, how's the universe going to end? If the center of all galaxies is black holes, and black holes have a really strong gravitational pull, and galaxies are really huge collections of hundreds of billions of stars, wouldn't that mean that logically the universe would pull itself together by gravity and result in a big crunch? This is what Stephen Hawking, very famous astronomer who died within the last couple of years, he had Lou Gehrig's disease, ALS. So one possibility is that the universe would end as a single gigantic black hole. Okay? So just like spacecraft have to exceed a certain velocity to escape Earth's orbit, it is not a foregone conclusion that the universe is going to end in a big crunch. We need to continue to collect data on this. In order for the universe to end in a big crunch, the pull of gravity has to be ever so slightly stronger than the force of the expansion outward from the Big Bang. And based upon all the calculations that we've made up until this point, it very clearly seems to us that the expansion of the universe is more powerful than the pull of gravity. Okay? So if the galaxies in our universe don't achieve a similar escape velocity from each other, they'll eventually come together by gravitational attraction between them. But if they do have an escape velocity stronger than gravity, then you would see a big crunch. Okay? So, that was a lot of stuff in a short amount of time. Okay? So I want to go back to that video because we do have time for that video, and that video does show us some examples of modern research that has been conducted with modern telescopes about galaxies. And I want to make sure I get audio going here, because I don't have audio yet. This video was produced in conjunction with the Spitzer Space Telescope, which is an infrared telescope. It measures infrared light, which is just to the left, just to the lower end, I shouldn't specify left or right, just towards the lower end of the electromagnetic spectrum from visible light. And one thing that you're going to read about while you are at home this week, because remember, you're here in person one day this week and at home 4 other days this week, you still have work to do. One of the things that you are going to be investigating is the different types of telescopes that astronomers use to learn more about the universe. Okay, let's see how the audio goes with this. And go.
Hi. Oh, good. Well, we are ready to begin.
Do you want to sit here?
Oh, that's perfect. Are we pre-rolling? Great. Great. Okay, so why don't you just introduce yourself?
Funky.
I'm Felicia Day. You hired me?
Of course. Is this your first time doing an internet video, Miss Day?
No.
Great, well then you know how this works. NASA's Spitzer Space Telescope has been studying galaxies colliding, and they've hired us to make an educational film to promote it.
Sounds good. I haven't read the script yet. They just gave it to me a few moments ago.
Roll camera. Let's try and get this in one take, people. Flunky, put up the image. And action.
Hi, I'm Felicia Day. As you know, colliding galaxies sure are scary. They're scary.
The script is down here. Nada here.
But now, the Spitzer Space Telescope has made discoveries that shed new light on the supernatural phenomenon. Okay, supernatural is a bit much.
Cue the graphic.
Was that an explosion?
That, Miss Day, was the sound of millions of voices crying out in terror and suddenly silence.
Star Wars
In other words,
reference.
galaxies colliding.
Do you even know what it means for galaxies to collide?
Well, I'm sure it's something like when cars collide, only, hundreds of times bigger. And we are on the timetable here.
So the humor is kind of sarcastic here, okay? So remember that galaxies are much, much larger than a star system, okay? I don't even want to assign a factor to it because it's so large. Note that our solar system is about 1 light year across, including everything, including the Oort cloud, including the Kuiper belt, all those outermost objects. And our galaxy is 100,000 light years across. So galaxies are ridiculously larger than solar systems.
Okay, first of all, galactic mergers are pretty common in the universe. Most large galaxies are formed out of smaller galaxies merging together.
Fascinating. Again,
The point is that you seem to think that it's destructive, like millions of stars smashing into each other. But in reality, there's so much space between stars that it's extremely unlikely that any two of them would ever collide. So while gravity may toss them around into new orbits, they'll all pretty much survive intact.
okay, fine. Funky, who is the explosion? Oh, yeah, much more dynamic.
I actually think it looks pretty cool.
I'm hearing a lot of talking and not a lot of script reading.
Okay.
So if you think of the analogy that I drew of mixing two cereals together, it's not like when you pour the two cereals together, the pieces of the different cereals explode when they run into each other. They just basically mix together, and gravity pulls those stars together, but it also can result in repulsions that prevents them from slamming into each other. Oops, darn it. Oh, all right, hold on. I gotta figure out how to work video in a slide, my bad.
You and Sean. So we,
Oops.
Let's see, galaxies are scary. Oh, okay. Here we go. But I'll bet you'll want to know what Spitzer has discovered, right, Sean Astin?
I like stars. Insert tape number 2.
Okay, so oh darn it! I just want to pause it. How is that? How is that difficult? So just to remind you, hey Angela, can you put your phone? Okay, there's a clock right there. And so Sean Astin was Samwise Gamgee in the Lord of the Rings trilogy. He was also Bob on Netflix's Stranger Things season 2, I want to say. Yep, season 2. So that's how you might know him. The joke here, obviously, is that they're using an audiobook for a guy instead of hiring him.
Tape number 2.
What in the name of Joss Whedon was that?
We couldn't afford to hire both you and Sean, so we edited together one of his audiobooks.
Haha, he reads Jane Eyre.
Here, Sean asked him again.
I like stars. Insert tape number 2.
Boy, I like stars too, Sean. But did you know that the Andromeda Galaxy is actually on a collision course with our own galaxy, the Milky Way?
Wow, what will happen then? My friend Felicia update.
I'm glad you asked, Sean. When our galaxies collide, all life on the planet Earth will be wiped out, and, well, that's just completely wrong.
Cut! Misty, how many North Pasadena Film Festival awards have you won?
Well, I haven't really... Oh, okay. That's very impressive.
So why don't we leave the film directing to the professionals, alright?
I just don't think you quite have a grasp on the science. Here, let me help. Flunky, can you put up the Spitzer IRAC picture of the Andromeda Galaxy, please? Andromeda is about 2.5 million light years away, so it's not going to collide with the Milky Way for a very long time.
How long?
Opinions vary, but an estimate puts it around 3 billion years.
Notice how this image of Andromeda looks very different from the image of Andromeda that I showed you before. The first image that I showed you of Andromeda is a visible light image of Andromeda. This is an infrared image of Andromeda, essentially a heat signature image of Andromeda. And you can learn different things from different images based upon the form of light that you collect from.
That's a lot of buildings.
Yeah, 3. The point is that we don't have to worry about it anytime soon. And when it does finally happen, the worst thing we have to worry about is our constellations getting mixed up a little bit.
But I like our constellations.
Stars are always moving, so it's not like our constellations stay the same for very long anyway.
You're really messing with my G.
You know what's great about this picture? Is that we can see a hole in the bottom right of the galaxy. Astronomers think that's where another smaller galaxy already collided and punched through Andromeda. Again, the stars weren't destroyed, gravity just moved them away, and...
Okay, I got it. We're not all gonna die. Once again, Felicia Day sucks all the excitement out of our film.
Well, I didn't mean to do that.
You know what, we'll pick up on page 3. Let's go, people, we are losing daylight.
You know we're indoors, right?
Action!
Oh, no. Oh. But what happens to the central cores of galaxies when they collide?
Do they blow up? Felicia, hi, I'm Sean Astin.
No, they don't blow up, Sean. But some people believe that the 2 supermassive black holes in the centers of these galaxies will try to consume each other, creating a time paradox. Okay, is there really anybody who believes that?
Oh, please, Felicia Day, correct us once again, that'll be so fun.
There might be supermassive black holes in the centers of some galaxies, but they're not going to create time paradoxes.
Like anyone's going to journey to the center of the galaxy and prove us wrong.
Okay, let me show you something. Flunky, can you put up an image from Dr. Henrik Stone's research? This is an artist's concept of something that Spitzer discovered a little while back. Spitzer detected the formation of tiny crystals in the centers of some galaxies.
Crystals? Like diamonds?
More like crushed glass. It was the first time that silicate crystals had been discovered in a galaxy outside our own. When the galaxies merged, the crystals were kicked up into a virtual sandstorm of dusty glass, enveloping the nucleus of each galaxy.
What she doesn't say is that infrared telescopy using infrared can help you to know exactly what compounds and elements are present in the largest amounts in different galaxies.
Sandstorms of glass in the center of the galaxies. That is intriguing.
But just goes to show you, you don't have to make up explosions or doomsday scenarios to make science interesting. Astronomy is pretty interesting on its own. I think even Sean Astin would agree with me.
The Earth is blue and has clouds.
You and Sean are right. I guess I've just been so focused that I lost sight of what this film is really all about. The science.
Okay, so During the second half of class, we're going to now delve into this idea of how does one go about determining scientifically the likelihood of aliens in space. And if you turn to the very last page in your packet, there is the questions for the video that you're going to watch. And I'm going to define the first one for you right here, and then your job will be to focus on number 2 and 3 throughout most of the film. Okay? Take a break. When you get back from break, we'll write down our answer to number 1, and then we will start an even older video that does a really good job of describing the science. Thanks, everybody.